Welcome to The Explainer. If you've ever felt kind of lost in the world of amplifier circuits, well, you're definitely in the right place. Today, we're going to draw a map, a guide that'll take us from the basic why of amplification through its core components and right into the real-world challenges that engineers face every single day. I mean, think about it. How do you take a tiny whisper from a microphone and turn it into this wall of sound that fills the stadium? The answer, of course, is amplification. But as we're about to find out, it's not just about cranking up the volume. It's really a journey of clever design, a whole lot of critical choices, and some pretty unexpected hurdles. This quote right here from someone on Reddit trying to get their head around this very topic, it just perfectly captures that feeling, right? Amplifier design can feel like you're navigating a maze. So our goal today, we're going to give you that map. All right, so here's our game plan. First, we'll dig into the core problem that amplifiers were born to solve. Then, we're going to meet the transistor, the fundamental atom of all of electronics. We'll see how these atoms get built into these powerful building blocks called op-amps. And finally, we'll step into the real world and face the challenges that make this whole thing both tricky and really rewarding. Okay, let's just dive right in. See, to really get a handle on amplifiers, you've got to understand the fundamental problem they were invented to solve in the first place. Okay, picture this. You're trying to connect a microphone directly to a massive concert speaker. Now, the microphone, it's great at creating a detailed voltage signal, but it has very little muscle. It can't push much current. The speaker? It's the total opposite. It needs a huge push of current to physically move the cone and make sound. That resistance to letting current flow, that's what we call impedance. The mic has high impedance, the speaker has low impedance. You connect them directly, poof, the microphone's signal just gets completely swallowed up. It doesn't stand a chance. And that's where the amplifier makes its grand entrance. It's not just about making the voltage bigger. It's acting as a kind of an impedance bridge. It takes that high impedance, low current signal from the microphone and transforms it into a low impedance, high current signal with enough power to actually drive the speaker. It completely solves the mismatch. Okay, so how do we actually build this bridge? Well, it all starts with the most fundamental component in all of modern electronics, the transistor. At its absolute core, amplification starts with a simple circuit, something like this one, using just a single transistor. But, and this is where the magic really happens, how you connect to that one little transistor, where you put the input, where you take the output, which part you tie to ground, it completely changes everything about how it behaves. These are the three main ways to wire it up. Common emitter is your all-rounder. It gives you a nice boost in both voltage and current. Common base is like the specialist. It really shines when you're amplifying very high-frequency signals, like in a radio. And common collector, often called an emitter follower. Now, this one is fascinating. It doesn't increase voltage at all, but it is brilliant at providing current gain. That makes it a perfect solution for that impedance matching problem we were just talking about. And that right there, that's the key takeaway. There's no single best configuration. It's never about which one is best. It's always, which is the right tool for this specific job? Are you building a radio receiver? A hi-fi audio preamp? Each one demands a different tool. Okay, so designing with single transistors is super powerful, for sure. But man, it is detailed work. So modern electronics often uses a higher level of thinking, a powerful abstraction to get things done a lot faster. So enter the operational amplifier, or op-amp. Yeah, just think of it like this. It's a prepackaged, super high-performance amplifier core, all ready to go. It saves engineers from having to reinvent the wheel by designing these complex transistor circuits from scratch every single time. Look at this. Inside a tiny little chip just like this one, you could have dozens, maybe even hundreds of individual transistors all working together. All that complexity is engineered, tested, and sealed away, giving the designer one single reliable component to work with. Honestly, the Lego brick analogy? It's perfect. There are these standardized, predictable blocks that just work. With a handful of op-amps and a few resistors, you can build incredibly sophisticated circuits for pretty much any analog task you can imagine. Okay, so if op-amps are our Legos, what kind of awesome stuff can we build? Let's look at a couple of designs that are all about high-precision work. Okay, two of the heavy hitters here are the differential and the instrumentation amplifiers. Their superpower is noise rejection. They look at two inputs and they amplify only the difference between them, ignoring any noise that's showing up on both wires at the same time. This is absolutely crucial for pulling a tiny, meaningful signal out of a really noisy environment.
The instrumentation amp just takes that one step further. It's a souped-up version designed for the highest possible precision.
And here we have a perfect example of building with these Legos. The classic 3-op-amp instrumentation amp it's just a beautiful design, really. It uses 2 op-amps right at the front as dedicated buffers. This creates an incredibly high input impedance so it doesn't disturb the signal it's trying to measure. Then a 3rd op-amp does the actual heavy lifting of amplifying the difference. It's a perfect case of combining simple blocks to get performance that's way beyond what any single block could do on its own. Okay, at this point you might be thinking, great, just snap the Legos together and we're done. But this is where theory slams right into reality and the real world introduces a huge plot twist. Instability. All of a sudden, that perfect amplifier you designed, the one that worked flawlessly in the simulation, it starts making its own noise. It becomes an oscillator. And the culprit? Pretty much always, it's some unwanted capacitance hiding somewhere in your circuit. And this graph, wow, this shows you exactly what that instability looks like in the wild. That bottom line? That's the dream. Clean, perfect. But that top one, oof, that overshoot and those decaying wiggles, what engineers call ringing, that is the classic visual symptom of a circuit that's on the verge of going rogue. It's a huge warning sign. Now, what's causing it? Sometimes it's obvious, a component you put there on purpose, but so often it's something sneaky. It could be the natural capacitance of a long cable you're using, or the input of the next chip you're driving. It can even be so-called parasitic capacitance created by the circuit board itself. You know, the little copper traces just being too close to each other. And this is such a classic trap for young players. Your circuit might seem totally fine on the bench when you feed it a nice, steady DC voltage. But the second a real fast-moving signal hits it, bam, that ugly ringing we just saw comes out to play, and you realize you have a problem. And all of this really brings us to the core truth of, well, all engineering, but especially amplifier design. It is a constant balancing act. You might want more gain, but that can push your circuit closer to instability. You might want a faster response, but that can make it more sensitive to noise. You can't have it all. Every single choice is a trade-off. So there you have it. From that single, humble transistor all the way up to complex ICs, from the perfect world of simulation to the messy reality of stability, we've seen that amplifier design is a deep and fascinating field. It's a journey of trade-offs and learning to navigate them. Well, that's where the real art of engineering is found.